Welcome viewers to the 16th lecture of the series Spur and Helical Gear Cutting. So, in the last lecture we were discussing about the uniqueness of the locations of the gearboxes in case of Hobbing machine, and if you look at this was the accepted position and this was the changed position, and we noticed that the location of I in this particular position unfortunately is going to change the Hobb RPM, and that would result in a different cutting speed, and that is going against our basic resolution that one gearbox should affect only what it is intended to and nothing else. Change in speed should be controlled by the change in UV, change in speed. So, this is not acceptable. Let us take up any other positions which might be acceptable. What if we keep V here and I here? In this case, if V is changed, yes, it is going to change the Hobb RPM, and it is exactly meant to do so. Okay. From the motor we get some RPM, and from that particular RPM we are changing it to some other RPM and providing it to the Hobb. So, V is serving its purpose, but the problem is, as V is lying in the loop now between Hobb and blank, a change in V is definitely going to bring about a change in the RPM ratio of the Hobb and blank, which means that you are going to start cutting a different number of teeth, something you never intended to do, never intentionally wanted to do. So, V cannot be placed here because it starts interfering with the indexing or selecting the number of teeth for cutting. Another one, what about this? Can we have this sort of a location? V is in the correct position because a change in V changes the RPM of the Hobb, but I instead of this location has been shifted here. Does it cause any problem? It is still in the loop between the Hobb. Okay, if I pass between the Hobb and the blank, and therefore there is absolutely no problem, it can control the number of teeth to be cut. However, we see that it is also in the line between the blank and the vertical movement of the Hobb. This is a threaded element, a screw rotating inside a nut and configured in such a way that if the screw rotates and does not translate, and if the nut does not rotate but translates only, due to the rotation of the screw, the nut will suffer a translational motion, and accordingly the Hobb will have its longitudinal feed, vertical longitudinal feed. So, unfortunately, this particular longitudinal feed is going to be affected if we put I here, because it is defined as millimeters of Hobb movement per rotation of the blank. So, here we find once I is placed here and it is changed, okay, no matter that it will be definitely it will change the number of teeth to be cut, the purpose it is supposed to serve, but it is also going to change the number of millimeters per workpiece revolution, because it is simply going to change the number of millimeters you are moving with respect to the blank rotation. Therefore, this is also not affected. Why? Because it does change the number of teeth correctly, but it also affects the feed which it is not supposed to carry out. So, this is also not affected. This is also not accepted. What about this one? If we place S here It does control the number of millimeters of movement, that means longitudinal movement of the hob with respect to rotation of the blank. Okay, rotation of the blank, that is, in one rotation of the blank, how much is the job or the hob coming down. So, it does control it because it is in that particular line. With respect to the blank rotation, you can change those number of millimeters, you are bringing it by up or down. Unfortunately, it is now also in the loop between the hob and the blank, and therefore, it will start affecting the number of teeth being cut, which is not at all acceptable. Okay. Therefore, this is also not a correct configuration. Now, we will introduce in brief, in very simple language, the setup for helical gear cutting. What is helical gear cutting? For this, let us have a quick look first of all at on this particular figure. If I have a blank on which, if I have matched the rotational ratio of the hob with the workpiece, if this rotational ratio is matched, when say the meridional plane x comes under the hob, okay, it gives a cut. So, this way each and every, say, let us call these meridians alpha, beta, gamma, x, all these are going to get cuts which are going to be vertically downwards exactly, just because they are synchronized, they are matched, they are exactly given the rotational ratio that they are supposed to have. So, cuts take place this way, but in case of helical cutting, we want the cuts to take place this way. So, scientists, metal cutting scientists thought this way, I am moving down in this manner. I want to move down in this manner when I am cutting helical threads. So, it basically boils down to the addition of a velocity vector during cutting action. How do I provide this velocity vector? Can I provide it by making the hob move this way? But in that case, it will lose contact. So, this velocity vector can be provided by, rotation of the workpiece. The workpiece can rotate and therefore provide this velocity. So, an additional velocity will be obtained by rotating the workpiece, okay, so that the final resultant vector lies in the direction of the desired helix angle. This is the basic idea. How do I rotate the workpiece? Now, here I can point out one thing which you have to which you have to think about. I will say the workpiece is already rotating. The workpiece is already rotating. So, how come you are going to think of rotating the workpiece? Due by virtue of this rotation only, it is having synchronization with the rotation of the hob. So, this means we are basically talking of an extra rotation. What is this extra rotation? That means in addition to the rotation of the workpiece in order to synchronize with the rotating hob, I put some additional rotation. How much will be this additional rotation? This additional rotation will be such that one complete extra rotation will be carried out by the time the hob moves by one lead of the helix angle thread. Okay, let us have a look at it on the figure. this is our workpiece, and therefore, if we unfold the full workpiece, this comes out to be say pi d. Okay, circumference. Now, the helix should be such that this is equal to lead of the helix, and this we know as alpha, the helix angle, and therefore, helix angle is tan inverse pi d by L. So, alpha equal to helix angle. So, we have to find out how much is this motion downwards. This is the feed motion. I want to move this way. If I can move exactly pi d amount, that means if I can rotate once, by the time I am carrying out the lead motion, then my job is done. So, how many times in order to move pi d, okay, how many times does the job have to rotate? It has to rotate by 1 times only. 1 time single rotation, which is extra to the rotational motion it is already having. So, for this one rotation, we will ensure that lead amount of motion will take place for the worm gear. For the worm gear, for the worm. The worm, when it is being fed down, it will execute exactly lead amount of motion by the time the cutter, the workpiece rotates once. So, workpiece rotates once, lead of the helix is this much, that means cutter moves by that amount, and therefore, this helix angle will be established. Okay. So, having understood this, let us start doing some calculations. Oh, by the way, now if we look at the figure, in order to make this possible, that means in order to make this extra rotational addition possible, we are incorporating another separate line. What is the separate line? Since power has come up to this point, after which it enters a vertical screw, by the rotation of which this nut is moving downwards. Okay. There itself I have tapped the power here, and I have passed it through a gearbox and added up the result of that gearbox with the with the input coming directly from the motor. So, this is a feedback. This is called the differential gearbox. Okay. Sorry, this is called the lead change gears. I am changing the lead with this. That means different helix angles will be cut with the help of this, and this is the sign of summation. These two rotations will be added here. Now, how do you add rotations? Addition of two inputs to produce a single output is referred to as a differential process. The mechanism which does it, it is referred to as a differential mechanism. So, this represents a differential mechanism. Okay, differential mechanism. From the differential mechanism, the output ultimately passes through to the blank rotation and basically and this gearbox was already existing. So, these two inputs are added together and given to the workpiece so that it undergoes some additional motion. Okay, we will see how this works. So, we are now accepting that we have 1, 2, 3, 4 gearboxes and a what do you call it, an differential mechanism for adding these two inputs. Okay, this is the velocity relation which we have already discussed. That means the hob has downward motion and the blank will be given extra rotation, because of which there will be a tangential motion. The resultant of both the velocities will give rise to the helix direction. Now, a word about differentials. What is a differential? Differential can be the sun planet mechanism, where I am having this large orange colored gear which is having its own rotation. Okay, it is rotating. Who is it connected to? It is connected to another gear in mesh, and these two are pinned. Okay, they are having pin connection with an arm, this blue arm. So, I can rotate the blue arm also, which I have shown by a blue curve arrow. So, I can rotate the orange gear. Let us have a look again at the figure. I can rotate the orange gear, I can rotate the arm, and due to these two inputs, the output of the black gear will be defined, and therefore, two inputs are considered here, and there is one single output, rotation of this particular gear. Okay. This is a differential called sun and planet mechanism, and here we have another differential called the bevel gear differential. Let us see what is the scheme of operation. This is one bevel gear which is getting input from one source. This is another bevel gear which is getting its input from another source. Maybe ultimately they are drawing power from the same motor, but they are coming through different paths having different rates of rotation. So, these two bevel gears are rotating at different rotations per minute. What will happen if they have equal rotational value, but opposite in direction? That means one is rotating clockwise, one is rotating counterclockwise. What will happen to this gear in contact with them? In that case, this gear will remain in position and just rotate about its axis, because this is rotating say 80 rpm clockwise, 80 rpm counterclockwise. So, this will remain in position and rotate, because let us draw a figure. This is the figure. I have one gear at this place, yeah. So, I am rotating this one this way, I am rotating this one this way, and therefore, this gear will be rotating this way. Okay. If these are equal in magnitude, it will simply remain in position and rotate. But suppose I had rotated this one in this direction, what would have happened? Same rotation, both of them in the same direction. In that case, this would have been driven, round and round and round this way physically, and we would have noticed a rotation in this final resultant shaft, because both of them are moving this way, and therefore this gear is going to move this way now, and therefore this shaft would have rotated, okay, and this would have moved this way like that. So, by addition of these two input rotations, I can get a final output rotation here. So, having understood this, okay, we can move on to our final discussion about gear hobbing setup. This is a gear hobbing setup. Now, how is it different from this one that we have studied just now? This one is a schematic diagram where the details are not provided, but ultimately when we are discussing about gear hobbing, everything has to be considered. So, let us see what are the things that we are supposed to consider here. First of all, as we discussed, the motor, power source, single power source. From this single power source, first of all, let us locate the gear boxes. First gearbox that we should come across is V. Yes, UV is there, UV with yellow color. After that, there is a bifurcation here. Let us see, it is traveling. Yes, there is a bifurcation. There is a bifurcation here. What happens at that bifurcation? One side goes directly to the hob and the other side goes to the differential mechanism. Okay, let us track them down. Yes, one side is going to the hob and the other side is going to the differential mechanism. That is good. What is happening to this hob? It is connected to the workpiece and they rotate together, and this differential mechanism, let us see what is happening here. The differential mechanism gets one input from the motor, which is basically this one. It has another input coming from the lead change gears. It is having another input coming from the lead change gears. Okay, so, this is one input, this is another input, and the output must be, as we discussed, this shaft. Sorry, I made a slight mistake. The first input is this and the second input is through these two gears, 1 and 2, not this gear shaft in between, inside. What is this particular gear shaft then? This gear shaft must be containing the output, okay, the output. Where is the output going? In the schematic figure, the output is supposed to go to this particular index gearbox. Wait a minute, this index gearbox should have been here. Okay, that is good. We will be definitely matching and finding out whether we have by chance put the wrong figure. So, in that case, from here we are supposed to get the index gearbox. Yes, it should have been here. Okay. Shall I quickly make this change? Let me see how fast I can do it. Okay, I think this should suffice. I cannot remove this small line. How does it matter? So, this is the configuration which is correct. So, let us read once again: motor, UV, that is speed gearbox, bifurcation. So, there is the bifurcation here. One side goes to the hob, one side goes to the hob, one side goes to the differential, one side is going to the differential. Next, from the differential gets another input, the differential gets another input. This one, it must be from the lead change gears. Yes, it is from the lead change gears. The differential has an output. The differential has an output which is going to index gearbox. Yes, the differential is having an output which goes to the index gearbox. From the index gearbox, there is a bifurcation. from the index gearbox there is a bifurcation. Yes. Is there? Yes. From here it goes to the workpiece and it also goes to US. Bifurcation. Here there is the bifurcation. After this bifurcation, it reaches the blank on this side, it reaches US on this side, and from US it is supposed to come out. From US it is supposed to come out, a bifurcation is there. Yes, there is a bifurcation. One goes to UD, yes, one goes to UD, and the other one goes to the screw. The other one goes to the screw. Yes, the other one has gone to the screw. Okay. So, this figure is correct. It matches with this one figure. Now, let us see what we are supposed to do here. We are supposed to first of all determine, we have first of all decided, tested it and found out that everything has been correctly configured as regards the locations of the gearboxes. Okay. And next, let us take a numerical problem. You are cutting a 160 teeth right hand helical gear with normal module of 2 and a lead of 1000 millimeters on a gear hobbing machine. The ratios of the speed gearbox, index gearbox, feed gearbox and lead change gearboxes, determine the ratios of the speed gearbox, index gearbox, feed gearbox and lead change gearboxes given the hob is of 2 starts and should develop 140 rpm. All bevel gear pairs are 1:1 speed ratio. The vertical feed of the hob is to be 0.2 millimeters per revolution of the workpiece. Answers are provided. Answers are UV should be 1/8, index gearbox UI should be 5/8, the feed gearbox should be 9/10 and the lead change gearbox UD should be 3.2. Okay. So, once the answers are given, the figure is given, you already have prior knowledge of working out this sort of a problem on gear shaper. I expect that you will be able to solve this problem fully yourselves from the figure that I have given you just ahead of this one. So, today I am not formally solving it. In this lecture I am not formally solving it. I will take up the solution the next day. In the meantime, I would suggest that please try to solve the problem yourself, because you know how to solve this sort of problems from previous practice. Okay. Let us have a quick look here. For example, is there any mechanism which is not known to us how it operates? We have belt pulley, bevel gear, etc. The differential. The differential is something which is at present not known to us. I would suggest that when you are solving for the initial part of the problem, consider that you are not cutting a helical gear. By the way, have I provided the helix angle? I have not provided the helix angle. Can you guess how you can find out the helix angle? You can find out the helix angle from the value of the lead. Okay. We know tan theta equal to, that the helix angle is equal to tan inverse pi d by L. Okay. By the way, you don't yet know how to work with the differential. In the differential, I can suggest that when you are finding out the initial values, consider the output RPM of the lead change gears to be 0. And that way you can first set the values of V, I and S. That means UV, UI and US can first be found out by considering the output of the lead change gears to be 0 RPM. And then we will find out the final value of D. So, with this we come to the end of the 16th lecture. Thank you very much.